To conclude our discussion about triangles, I'd like to share with you a little bit about similar triangles and one of the theorems that we can use and find very useful. What I've drawn here are two similar triangles. Similar triangles, all three angles in the triangles are equal. So let's even presume that angle C is a right angle, which is not necessary. It's just that the angles have to be equal, but I'm just going to pretend that they are right angles. So if these are similar triangles, then angle C would equal angle C prime, and angle A would equal angle A prime, and angle B would equal angle B prime. Yet their sides are not equal in length, as you can see. I tried purposefully to draw these triangles, one a good bit smaller than the other, but the angles equal in size. But one of the things we know as mathematicians is that corresponding sides in similar triangles are proportional. So what I've written down here is that what's called AC, let's call this AC on the little triangle, corresponds with A prime C prime on the big triangle. And those corresponding sides in that ratio are proportional, or can be set equal to one another, and therefore a proportion. So BC, a different leg, if you will, because I decided to call these right triangles, would be corresponding with B prime C prime, and then the hypotenuse, and then the hypotenuse. I can write these ratios in a variety of ways. I think I'll stick some numbers on here. Say that this is 2 and this is 5, and say that this is maybe 6, then how big is this side right here? That's what I'm looking for. So I would say the corresponding sides, 2 is to 6. I like to write them like this, 2 is to 6. If I started in the little triangle, then I have to stay in the little triangle with this leg, and I have to say as 5 is to x. That's how I could write the ratio of these corresponding sides and set them as a proportion. Then I'd set this cross product, 30 equal to 2 times x, and then I divide both sides by 2, and I'd find out the side called x is 15 units. I love this tree example. I've even used it before in my backyard when I wanted to know the height of a tree but couldn't measure it, of course. So here's what I'm going to do. I'm going to draw the tree in my backyard. And then I'm going to draw myself, if you will, standing kind of close to that tree. So that's me. And then here's the ground. And way out here is a bright ball of sun in the sky, and I'm trying to look at my numbers to see how I want the shadow to be from the sun. So there's the bright ball of sun, and it's causing these objects to create a shadow on the ground. And pretend I'm not right behind the tree, but I'm off to the side, and so that my shadow looks, this line is parallel. These lines are parallel, supposed to be parallel. So this triangle of me is similar to the triangle that's created by the shape of the tree, because I've chosen to draw the ground at a right angle to the base of the tree and myself at a right angle, and then because of the sun, this angle and this angle are equal, etc. So I know that I'm 5 foot 6 inches tall. So I'm going to put that right here. That's me right here, 5 foot 6 inches tall. And somebody helps me out, and we measure that my shadow that is cast because of the sun is 2 feet 3 inches. And then the shadow that occurs because of the tree, this dimension line is very, very poor, is 16 feet. So I want to find out how high the tree is, h, right here. So I'm going to set the ratio of the height of the tree to my height. Hey, wait a minute, I'm 5 foot 6 inches. Why did I call that 5.5? So be careful. A lot of people would call 5 foot 6 inches 5.6, but there's 12 inches in a foot, and so if I'm 5 foot and I'm 6 inches, I got to divide that by 12, and 6 divided by 12 is a half. or 0.5. All right. The tree's height to my height has got to be set equal to the tree's shadow to my shadow, 2.25, because 3 inches out of 12, it's 2 feet 3 inches, would be a quarter of an inch. So I'm going to erase some of this. It's getting in the way. So now I'm going to set these cross products equal to one another. So this one right here, I'll have 2.25 times h equals 16 times 5.5. I believe I've done this calculation. I think so. When you multiply this together and you get approximately a little bit more than 80, maybe, yeah, a little bit more than 80, and then you divide both sides by 2.25 to get h alone, you should find out that the height of the tree is 39.1 feet, all by this similar triangles and corresponding sides. The ratios can be set equal to one another. Pretty cool topic. Here's another one that's pretty good. A state's automobile inspection program checks headlight alignment. The drop in the light beam cannot be greater than 2 inches for every 25 feet in front of the car. All right, let's just first think about that a minute. These are my tires. And let's do this. Whatever. I want my car going this way, so I'm going to put my headlights right here. So the drop in the light can only be 2 inches. For every 25 feet I go out, it can go down 2 inches. I'm going to put here 25 feet, and then here I'm going to put, when I can write it a little bit better, I still want to take this out a little bit more, 2 inches. Well, first of all, and then it says, suppose the headlights on your car are 27.5 inches off the ground. So, of course, this is not a proportional drawing. This is poorly done, but it's because of the pen I'm using and just my scale. But the distance from here to here is supposed to be 27.5 inches. First, it says, what is the ratio drop of the light beam, drop, 2 inches, to the distance in front of the car, ratio. So 2 inches to 25 feet. That's not cool. Not cool to have the units be different. So let's multiply 25 feet by 12 inches in 1 foot. So what I'd have is 2 inches of drop for every 300 inches I look forward. So that would be a ratio that I could use, because now what I want to figure out is, suppose your headlights were adjusted to that ratio, how far in front of your car would the light beam from your headlights strike the ground? So let's just use green, and let's go way out here, and that light beam's going to strike the ground. So I'm looking at this green triangle in comparison to this black triangle, the 2 inches and the 25 feet. And I know that I want this to be 27.5 inches, because that's how high they are above the ground. So again, if I have a 2-inch drop for every 300 inches out, then I want to drop 27.5 inches to get to the ground. So how far out, I'm going to put, can I go? And so there's my proportion. Again, drop over going out, and here's my drop over going out. When I set this product right here, 2 times x equal to this product right here, 300 times 27.5. If you would multiply 300 times 27.5, and then you probably get about 8,200 or something. Then divide both sides by 2, you would find out that your beam could go 343.75 feet, and I'm going to round that to 344 feet. Another use of triangles, similar triangles, in order to find a distance that might be inaccessible to me.